Hello and welcome back to the lab. In today's video, we're going to finish up work on the HP419A DC Null Voltmeter. When we left off, we had swapped out the NiCad batteries, rechargeable batteries, with some new batteries. And today we're going to finish up work on the batteries and the charger circuit. And we're going to take a look at the neons in the photochopper assembly. And hopefully we'll be able to get this magnificent old instrument up and running again. So stay tuned and let's go. Okay, so just to recap how we calculated the battery charger current, we have a 6.81 volt Zener diode and a base to emitter forward junction drop of about 0.7 volts. That resulting voltage appears across R3, the 560 ohm resistor. And if you do that calculation, that gives you the charge current for the batteries. In fast charge mode, the switch places this 750 ohm resistor in parallel with the 560 ohm resistor, and that increases your current, the same voltage across a smaller resistance. So let's do that calculation now. We have 6.81, base to emitter drop of 0.7, subtract, divided by 560 ohms. It's 10.9 milliamps of current in regular charge mode. And in the fast charge mode, we will, let's clear all. In fast charge mode, we have the two resistors in parallel, so it's the same voltage, 6.81, 0.7 subtract, product over sum, 560, 750 times 560, 750 plus divide, voltage divide, 19.05 milliamps in fast charge mode. So we have 10.9 milliamps or 19.0 milliamps. So that's the two charging currents we'd expect to see on the batteries. Now I thought this would be a perfect time to use my clip-on 428B clip-on DC milliammeter that I worked on in a previous episode. So I will clip that on to one of the battery wires, and we'll see what current is actually flowing into the batteries from the charger circuit. I'll be right back when I've done that. All right, so I've hooked up my 428B clip-on milliammeter to the 419A's positive 12 volt battery wire. See the red wire in there? The clip-on probe is clipped around it. And the first thing I want to do is, without the instrument plugged in, I want to turn the instrument on and see how much current the 419A will draw from the batteries with it unplugged. So let's turn it on, see how much current is drawn from the battery without the charger circuit enabled. When I switch the voltmeter, the 419 to voltmeter mode, it looks like on the 10 milliamp range we are drawing 6.1 milliamps of current. So that's how much current is coming out of the batteries. Now, when we plug the instrument in, we should have more current going into the battery than what is coming out of it. So let me see how much current is charging the battery once we've plugged it in. Now remember, we calculated 10.9 milliamps. So I'll plug it in, and now I'm going to turn it on. And, well, it's going in the negative direction. Well, that makes sense because there's not current flowing out of the battery any longer. There's current flowing into the battery. So let's turn the probe around so that we're measuring positive current. There we go. Now, current flowing into the battery looks like it's about 3.9 milliamps. And if you do the calculation, 3.9 milliamps plus 6 milliamps is 9.9 milliamps. We're off from our calculation of 10.9 milliamps by about a milliamp, but still pretty close. We're off by about 10% on our calculation. So when the instrument's plugged in and operating, the batteries are charging at only a 4 milliamp rate in slow charge mode. When we switch to fast charge mode, meter off scale, it looks like we have a net positive charging current of 16.5 milliamps, plus the 6 milliamps that the instrument is drawing. So we should have 22.5 milliamps of total current. And we calculated 19. So we're a little bit higher than what we calculated. About 22.5 milliamps actually is what's flowing into the battery, less what's flowing out of the battery to operate the instrument. So our calculations were a little bit lower than what we're actually getting. So I guess that's good. That's good. So we have a net charging current of 16.5 milliamps, even with the instrument operating in fast charge mode. Okay, very good. So does the instrument work? Well, of course it does. I wouldn't be recording a video if the instrument was still broken. Plus, if you look at the thumbnail at the beginning of the video, you can see the 419A actually making a voltage measurement. So obviously I did get the instrument working. So let's take a look at the front panel now and play around with this instrument now. Well, I think I've gotten a little bit ahead of myself here. Before I play around with the instrument and make some measurements, I wanted to take a closer look at the photochopper block and actually see what the waveforms are coming out looking like on the photochopper, and actually take a peek at the neon bulbs and see if they actually are flashing. I imagine they are because the instrument seems to be working. But let me turn off the lights in the lab, and we'll peek in and see if we can see the neon lights illuminating. How about this? If I turn this one off, and here we go. You look down in there, down inside. It's not really focusing very well. There it goes. Right down in there, you can see the neon lights are indeed flashing. They seem to be flickering a little bit. Not surprising. They are 60 years old, those bulbs there. I'm sure they're beyond their useful life, but they seem to be illuminating. And let me show you on the schematic what this photochopper is and what it does, and then we'll take a look at the waveform for the driver circuit for these neons. We'll see if that is within spec in terms of frequency and amplitude, and maybe we can do something with those bulbs. I'm not really sure, but we can try. All right, let's do that. So taking a look at part of the schematic for the 419A, the photochopper assembly is really the heart of this instrument, and as well as many of Hewlett Packard's earlier instrumentation. The photochopper is in two parts. There's the modulator part, which is this part over here, and there's the demodulator part, which is this half over here. Even though this is a DC voltmeter, it measures DC volts, the main amplifier circuit in the instrument is an AC amplifier. In fact, it's coupled at the input with this 0.1 microfarad capacitor, and it's coupled at the output with this 1 microfarad capacitor. So it's a DC amplifier between here. It's an AC amplifier between here and here. DC arrives at the input and is chopped up by this input photochopper, which is these two photocells, which are illuminated by alternately flashing neon light bulbs. And these photocells increase or decrease their resistance in such a way as to produce a square wave at the output in response to the DC applied at its input. So there's an AC square wave at the output of this modulator, half of the photochopper. At the other end of the high gain AC amplifier is the demodulator over here, and these do the exact opposite. They sample the high and low values of the square wave after it's been amplified and convert it back into DC. So the second half of the instrument is a DC coupled amplifier, but this is a low gain amplifier, not the high gain amplifier used in the AC portion of the instrument. Now, these photochoppers are driven by neon light bulbs, and those neon light bulbs, they burn out over time, and that's probably what has happened in this instrument, although they seem to be working quite well, and I may decide to just leave them. If I can get the waveform for the driver to match what it's supposed to be in terms of amplitude and frequency, I will probably just leave them, even though they seem to be flickering and not really responding in the appropriate manner. Let's see what we can do with that. So I've hooked my scope up to the test point on the A2 assembly that is used to check the current and the frequency of the neons, and should be 150 millivolts for the one peak and 75 millivolts for the other peak. Now the 150 seems right, but the other neon is flashing is drawing more current than it's supposed to be. So those neons aren't very well matched. This is closer to looks like 85 or 90 milliamps millivolts of voltage on this waveform. The frequency seems correct, and you can also see on occasion, I don't know if it shows up in the video because of the weird strobing effect from the frame rate of the camera, but there's occasional dropped or missing pulses where the neon fails to flash, fails to fire at the appropriate time on the waveform. That happens every once in a while. It's not surprising. These neons are very old. Let's open up the photochopper and pull the neons out and take a look at them and see if we can notice anything physically on the neon bulbs. All right, keep in mind that we're dealing with neon light bulbs here, so there is a voltage of approximately 90 or 100 volts in this circuit. So make sure you have your instrument unplugged. You don't want to get zapped. All right, and to access the neon bulbs inside the photochopper, you remove the two screws on the side over here, and the photochopper block can carefully pull out, and those neons are tucked inside. Let me show you that. Okay, so after removing the two screws from the side that are holding the neon chopper assembly on the side of the instrument, we can carefully remove the chopper block, and inside is a circuit board with the two neon bulbs soldered onto it, and also some a few other components, some resistors, some diodes, and a capacitor. These are all for timing of the instrument to make sure that they flash at the appropriate rate. Now, looking carefully at the bulbs, I can see that they're a little bit blackened, because there's a lot of life. They've been running for a very long time. They've been running for 60 years. I'm surprised that they work at all, actually. Um, they seem to be working quite well. I could try to swap them out. I do have replacement neon bulbs, but it's very tricky to get a matched pair of bulbs that will work properly in this instrument. Um, I may decide to just leave these bulbs exactly the way they are. Even though there's a little bit of occasional flickering with the bulbs, they don't flash at the correct times every single cycle, but they seem to be working quite well, and I have a feeling I might end up making the situation worse um, by trying to change them out. I think I will give it a shot, but I will save these old neons and just put them back if I can't come up with a pair that works properly in this instrument. Let's give it a shot and we'll see what happens. Okay, so I removed the neon board from the photochopper completely and um, set it up in my Panavice circuit board vise, right, so that I could take some time and swapping out the neon bulbs to try to find a pair that will work without minor fluctuations or occasional intermittent flickering of the neons. And I think I found a pair that works. Um, and I've tried to do the adjustments up here for the frequency and for the amplitude of the waveform on the test point. I have my scope clamped onto the test point there. Um, the frequency is correct, and the pot that adjusts the frequency is almost all the way to one side, but it's still, the frequency is within tolerance, so that's good. And the amplitude, in order to make it work properly, I had to dial up the amplitude a little bit higher neon current than is recommended by the manual. You're supposed to have 150 millivolts on the test point, and I have about 200 millivolts peak to peak of the waveform in order to get the neons to flash without flickering and to have a beautiful consistent waveform without any intermittent flakiness going on there. So hopefully these neons will be better than the 60-year-old neons that were in there originally. They seem to be visually, they seem to be much better. We'll have to see how it works when I get them installed back in the photochopper. If worst comes to worst, I can put the original neons back in. But I swapped out combinations of like 6 or 7 different combinations of neon bulbs before I arrived at this combination that seems to work the best. Um, it's a painstaking process, um, but hopefully this will work out. Let me show you what the waveform looks like with these neons. Now, again, the flickering that you may see on the screen is not um, due to the neons. This is just the frame rate of the camera interacting with the sweep rate of the oscilloscope. But you can see that the peak-to-peak amplitude of this waveform is about 200 millivolts peak to peak, when in fact it's supposed to be 150 millivolts. So we're really running the neons at a pretty high current above what's recommended. But the second neon, one half of the waveform is for one of the bulbs, and the other half of the waveform is for the second bulb. And it is, in fact, half the amplitude of the other neon. So that's what it's supposed to look like when it's functioning properly. So hopefully the fact that it's 200 millivolts instead of 150 will just make it work a little bit better. We'll have to see. Okay, so with the new neons installed, I buttoned the whole instrument up. I didn't even do the adjustment procedure except for the neon adjustments. Other than that, I left all the other alignment pots just exactly the way they were set when I received the instrument. And now we're ready to do some testing to see if it works. Of course, it does work. You know, I've tried it already. So my 740B DC standard is still not working. I haven't fixed it yet. So I am using just a standard DC power supply, an HP 6205C actually, with 3455A digital voltmeter across it. And that will be my voltage standard for inputs, at least for the higher voltage ranges. Let's try 1 volt DC and see if it works. Or I hope it does, because it was working before. Dial it up. Oop, we got it negative here. Let me turn it around first. Okay, the power supply is set to 1 volt exactly. Looks like the instrument is reading very, very close to 1 volt exactly. In fact, I would say, I don't know, the needle, there's a little parallax on the camera, but the needle is lined up precisely with the 1 volt mark to my eye. I think it's exactly 1 volt. Now flip the polarity around and test negative 1 volt. Again, looks like exactly negative 1 volt to me. Very good. All right. We can go up higher. Let's go to the 10 volt range. We can put 10 volts into it. Okay, my power supply is now set to exactly 10 volts. The meter looks like it's reading 10 volts. Again, flip the polarity around, look at negative. It looks like negative 10 volts to me. Very, very good. All right, for the lower voltage ranges, I don't have a precise DC standard to calibrate this instrument with, but what I do have is some precision resistors that I can use to make a precision voltage divider. So that's what I'm going to do. I'll come back in a second with that setup. Okay, so first let me show you what the test setup is here. We have two precision standard resistors, two general radio standard resistors, type 1440 if you want to know the model number. Down here is a 100 kilo ohm resistor, and up at the top is a 0.1 ohm resistor, 1/10 of an ohm. So what we really have here is a voltage divider that's set to divide by 1 million. So if we put in 1 volt through the input over here, by the time it gets to the 419A input terminals, it's 1 microvolt. So we can test the very low voltage ranges on the 419. If we put in 10 volts, we will have 10 microvolts, and so on and so forth. So that's the setup, and so let's go. Let's try 10 microvolts. First, we want to 0 Actually, it's best to zero just with this setup because we have a 0.1 ohm resistor across the input terminals. It's equivalent to a short circuit. So we can zero the instrument without even checking the zero function. It's best to really zero with a short on the input, not shorting with the zero function, because what you actually test that way is the complete circuit all the way through to the input terminals. So if there's any thermally induced EMF or anything like that on the input, you will take that into consideration when you make your zero adjustment on the front panel. Switching to zero will not take into account what's happening out here at the front panel. So it's best to just zero it with a short across the input, or in this case, a 1/10 of an ohm across the input. All right, so very sensitive, but we are just about at zero there. Okay, so let's turn on the voltage, and we want to put in 10 volts in order to get 10 microvolts. So let's do that. 10 volts will be right there is 10 volts. And it is in fact reading exactly 10 microvolts. I think that's just amazing. Let me flip the polarity around and look at negative 10 microvolts. That looks like negative 10 microvolts to me. We can check the very lowest range by going down to 3 microvolts. Let's first start by going to 0. Readjust our 0. Very sensitive adjustment. Oop, a little bit too much. Come on back. Very close to 0. Very close to 0. All right, now let's turn on our voltage. We want to put in input of 3 volts to get 3 microvolts across the input of the 419A. And 3 volts on the input is right here. It should be reading 3 microvolts. It's reading exactly 3 microvolts. That is just simply amazing. If I turn this down to 1 volt on the input, we should be reading 1 microvolt on the meter. Here's 1 volt. Should read 1 microvolt. It looks like 1 microvolt. If I drop this input down to 1/10 of a volt, we should be able to read 100 nanovolts on the meter. Let's see if we can do that. Oops. There's 1/10 of a volt right there. Should read 100 nanovolts. I think the meter reads 100 nanovolts. Isn't that amazing? It's a little bit noisy down here, but it's definitely reading 100 nanovolts, jumping around a tiny bit. Positive 100 nanovolts. Let's flip the input around, see if we can get it to read a negative 100 nanovolts. There it is. Again, a tiny bit noisy, but it is definitely reading negative 100 nanovolts. All from an instrument built in 1965. And all I ever did to it was put in new batteries and a couple of neon light bulbs. I am very impressed with this beautiful old instrument. All right, what's left to do? I have not put in the null battery yet. I still have a battery holder uh, to put in here. I haven't it on order. I haven't received the battery holder yet, so I haven't been able to put in the null battery. So I haven't been able to check to test the set null and read null functions of the nulling part of this instrument. But the regular voltmeter is very, very sensitive. It reads down to 100 nanovolts of resolution. Pretty amazing. All right, well, that will do it for the 419. Um, when I do get the null battery installed, I'll do a very short follow-up video demonstrating the nulling function on this 419. But the rest of the instrument is finished and calibrated and ready and good to go and ready to use. So thanks very much for watching and for giving me the opportunity to share my hobby with you. Please like and subscribe and stay tuned for more fun videos with vintage Hewlett-Packard test equipment and other fun stuff. Thanks again.